So, like I was just kind of saying, like, if you guys watched, quick thumbs up. Who did watch the playlist video? At least one of the videos. Did everyone finish the playlist? Everyone's gonna finish it. All right, cool, awesome. Yeah, that three blue, one brown playlist definitely is like totally worth watching. So anyone in the future watching this recording, go watch that playlist. I think it does a really great job of visualizing like the neural networks, the idea of backpropagation, as well as showing the mathematics, so you can follow along with it. I think it's a great supplement. So today we're gonna kind of go back into neural networks, right, and talk about all that good stuff. One thing, so I'm gonna kind of go through a little bit of what this next, like this session and then like next couple study groups, what kind of my plan is, and you guys can kind of like let me know. And basically the next few study groups are a little less structured in the sense of like, this is section 40, this is section 41, 42, kind of mentioned this before. Today we're gonna kind of go into neural networks, formally talk about like different parts of it. So last time we talked much more conceptually about all the different kind of like what it's done, like the motivation for it, like from the mathematics and stuff like that. Kind of botched that kind of explanation, but that's kind of there, like why we can use neural networks. So we'll talk about the different parts, and then we'll go into implementation. So we'll talk about the different parts are kind of like like weights, layers, batches, what that means, other hyperparameters, why we call it hyperparameters, activation functions. We'll talk about activation functions and what tends to work really well, at least based on the current research that I'm familiar with. So we'll talk about that. And then we'll go into, I believe we'll go into the Keras implementation. So we'll show you actually how to write neural network. If you guys have done section 40, I think section 40 like makes you do it by scratch neural network. For the record, unless you're doing research, you're probably never going to have to write a neural network by scratch ever again, unless someone like forces you to do, basically. And I think that's for the best. I don't think it's worth writing it from scratch. Me personally, I just think that's something that's like not necessarily like, I think it helps to understand the mathematics, but to write your own, it's kind of, in my opinion, useless unless you're really trying to make an optimized version. So we'll mostly focus on Keras, and specifically I'll be using TensorFlow, which is a library, open source, and Keras, which basically is kind of like an API that can basically attach to TensorFlow. It's actually built into TensorFlow. There are other frameworks as well that use in libraries, even in Python, or especially in Python, that can do like deep learning neural networks. One really like, you can think of like TensorFlow's, I wouldn't say it rival, it's just like another implementation is PyTorch. And it's just different. But I would say is that if you're familiar with Keras and like understand how this kind of works, you can very easily kind of switch over to PyTorch and understand how that works. There's a little bit of difference between the two. I will say, at least in the current state that TensorFlow and PyTorch is used, TensorFlow tends to be a lot easier to what we call put in production, so and deploy. So we can actually take those models that we develop as data scientists, package them up relatively easily with TensorFlow, and pass them on to software engineers to basically integrate it into their product. PyTorch, you can do that. It's a little like, it's not thought of as much as TensorFlow had been in that way. And so they basically piggyback on top of TensorFlow's implementation to make it work, which is kind of a hacky way. I mean, I don't know, maybe I'm not the best person to say it, explain it like this, but I think of it kind of like a little hacky way. It does work. There are companies that use PyTorch in production. For example, like Tesla's Autopilot is written in PyTorch. But if you're looking to say, oh, I want to do deep learning in like my data science position, stuff like that, like, should I learn PyTorch or TensorFlow? Honestly, if you learn either one and you are good at, like, well-versed in one of those things, you're going to be fine. You're going to find, like, even if a company uses another programming language, like, especially as your first, like, if you're looking for jobs or going in for like your first year as a data scientist, you're not going to have to worry about those like differences and stuff like that. Like, because at worst you learn on the job and you guys will learn perfectly fine. Okay. So that's kind of like what we'll kind of talk about today. If we have time, we'll kind of start talking about optimizations. So saying like how we can help neural networks learn faster, better, stronger, all that good stuff. And we'll continue that into next week on next week's study group on Tuesday. We'll kind of finish up optimizations a little bit on there. And we'll kind of talk about, it's technically an appendix of the curriculum, which is convolutional neural nets and transfer learning. That's kind of at the goal of like next time. We could talk about it today a little bit if you guys really want to, but I think it's worth kind of just showing a neural network and then talk about other specializations. The reason why I'm going to talk about convnets and like convolution, neural nets, CNN, convnet, they're all the same thing, and transfer learning is because transfer learning in particular is super useful as a tool and understanding how to use transfer learning to do like basically produce good models. And convolutional neural nets are usually associated with image recognition, but they're not the only, like, that's not the only use case. You can use convolutional neural nets to find other patterns and stuff, and we'll talk about that. And then as we finish up that, so hopefully by the end of next study group, we'll be done with convnets, transfer learning. We might bleed into the next one, which is Thursday. But if we're done with it, the goal should be going into NLP. So we'll introduce NLP, kind of going a little bit away from deep learning for a second. And then I'll kind of mention, as we're talking about deep learning, of like how neural networks and deep learning can be incorporated into NLP. So that'll be kind of like what we'll do on that Thursday. And after that Thursday, really, like, even though you guys would still have section 43, which is like AWS cloud infrastructure, that kind of stuff, you really have everything you need at that point, assuming you're following along, to do, what's it called? To do your Mod 4 project. Like, you don't really, like, I don't expect you guys to necessarily use cloud infrastructure, PySpark in your Mod 4 project, maybe not even necessarily in your capstone. We can talk more about that stuff. So on Thursday, we might even take some time to just kind of introduce briefly what the mod project is, what kind of you can do with it, and you guys can at least kind of like start working on it. The study groups after that will still kind of talk a little bit. I'll probably talk a little bit about more pipelines, because pipelines are amazing and you should be using it for your projects. But we'll talk about pipelines. We'll maybe talk a little bit about PySpark or containers, at least more of the big data stuff. I want to kind of maybe talk about that a little bit more just so you guys are familiar with it. And then maybe we'll also talk about cloud infrastructure like AWS, but it'll be a lot more free form versus like a structured notebook of like here for AWS. Okay, sound pretty good? Any questions of like those next few days? Yeah, Jessica.
Are we also going to be going over NLP?
Yeah, so NLP will be kind of on that Thursday
Okay, cool.
that we'll talk about. And to be frank, there's so much more we can do about NLP too. So as especially we get into like office hours and stuff, and you guys are like, oh, we don't really need to talk about the project, but we want to know about these subjects, we can talk maybe more deeper about that stuff. So like, for example, like we can talk about recurrent neural networks in LSTMs and stuff, which is technically in the appendix. The reason why I'm putting it off is because I don't think it's a necessary part for Mod 4 project if you are going to go NLP route, but it is good to know like what are the technologies and what are things that are being used, because really LSTMs are kind of like, LSTMs and grooves are basically like the thing you would use for NLP basics. Like almost no one uses recurrent neural networks in its purest form for NLP anymore. Researchers, things change very quickly, right? So we'll talk a little bit about that, like probably after, once you guys start the Mod 4 project, if that makes sense. Cool. And of course, if you guys find other subjects too, as we finish Mod 4 and go into Capstone especially, and you're like, hey, I heard about this thing and I want to learn more about it, definitely message me. Maybe we can talk about it for Capstone stuff. So I can't say I will be an expert in it, but I can do my best at least so we can talk about it and explore it a little bit. Okay, cool. Any other questions before we move into today's material? All right, cool. So let's get right into this. I'll share my, share my screen. There we go. Oops. I have too many windows open, so I couldn't find the window. There it is. All right. You guys can all see that. It says Jupyter, lists some stuff that's in here, some running notebooks. All right, cool. So again, like as always, you can find this on like the repo, right, on neural networks and online on GitHub. So I always put like a little link in there, but I think you guys all know where to find it, right? Like if you guys need to. Cool. All right. So last time we talked about, oh geez, sorry, there's a, my little bar was blocking it. All right. Neural networks. So last time we talked about neural networks, I kind of gave you guys a little bit of perceptron, understanding what that is. We actually skipped to the end even to kind of show you what tensor or like what a neural network looks like when it's training. We might actually revisit that later today. And I kind of motivated a little bit with talking about like you can implement logical like gates with neural networks. To be frank, I kind of botched that. I kind of forgot to tell you guys about activation functions, which made it really confusing on how to make this work. But the main thing you have to know is like, oh, you can basically say, hey, for these inputs and outputs, we can design a function that actually can determine like, oh, you know, actually reproduce certain actions that we could like hard code. And that's kind of the idea of neural networks in general. And so one thing you can think of neural networks, I think I have it later on here. Neural networks are something called can be a universal function approximation. So it basically means that if you can make a function of it, like a neural network can technically be that function. So basically, like if you can think of anything that could, like if you can design any function, a neural network can become that function. Now, there's a little hint to that. You're like, wow, that's pretty powerful. That's really awesome. Like, why don't we use neural networks for everything? The problem is finding the right neural network and finding the right, like values and stuff to make it work is not always easy. In fact, it can be very, very difficult. And so it might not be worth your time trying to design a function where in reality, you could have probably just coded it yourself. So this is where I like to say is like deep learning especially, it's not always a solution. Sometimes it is a very good solution. There's nothing better than that. But it's not the solution that you should just say, oh, I'll just throw deep learning at it. Unless you're a venture capitalist, and then you get lots of money because you say deep learning and stuff. So that's kind of like a review from last time. So I'm gonna skip over, we saw this kind of thing with the mathematics. It's basically just linear algebra. I think Jessica even mentioned about saying, it looks like, I think Alvaro or Jessica talked about linear regression, or maybe I mentioned it even, and Jessica mentioned about saying, oh, could we have like x squared terms and stuff like this? And technically we can, but they just would be like x3, and x3 would be equal to x1 squared or whatever. So it's kind of like feature engineering. All right, so let's talk about the actual parts of a neural network. So we kind of saw what this looks like, which is this guy right here. And we talked about these latent features. Really, they're called hidden layers. We'll talk about that. And so it's kind of useful to go through. So we have the input layer. And the input layer basically is like the initial features we're feeding in, the initial parameters that will be part of the network. And so you can see right here, these would be like the input layer. Easy enough. It's the layer, and we can think of like these vertical slices, right? This is the input layer. So this is the next layer over here. And so this next layer is actually a hidden layer. So basically this hidden layer is kind of like the stuff before the output, okay? So basically you can think of like when you design latent features. And I mentioned like, even though we have this guy right here, which kind of looks like relatively explainable, if you really built this neural network with these, I'm just gonna close this guy right here so we can actually see things. There we go. Okay, you can see right here is the output on our sales. This is more like a regression model than versus like a classification. But like this hidden layer basically holds like these latent features. These latent features, number of people that walk by, affordability, are not necessarily going to be very human-like. Like it just is whatever features made sense to make this work. And so a lot of times you can't actually look at these layers and understand, or these neurons and understand what's going on. And that's kind of a little bit why we call it a hidden layer. It's hidden within the network. And you might have heard people talk about black box, like a black box model. Give me a thumbs up if you guys are familiar with black box model. Okay, so just to review it, black box model basically means like you put stuff in the black box, stuff comes out the black box, but how the black box works is kind of unknown. You can investigate and look at all of these different weights and know exactly how, like, write the equation for this, but why the equation exists in this form is kind of not super clear. It's kind of like it's that way because it works, and that's kind of the idea of a black box model. So neural networks are like this. Okay. So anyway, this inner layer is a hidden layer. You can have multiple hidden layers, like I think I showed right here. Here's the input layer, first hidden layer, second hidden layer, right? And then the last one is our output layer. And the output layer, in this case, is just one value, but it could also be multiple values. And if we had multiple values, it would be like classification. Okay. So saying, oh, it's like, is it a dog? Is it a cat? Is it, a person? That would be like a classification output layer. But it could also be like, you can see like this is like Y. It could just be like, oh, what is the sales price of this house, right? It could be a spectrum, which means this value, this number right here can be any value. Well, I say any value, but like a spectrum of values. Okay, cool. All right, so those are different parts. That's pretty understandable, right? Those different layers. Yeah, okay. So that's what we mean by layers. I want to make this not so much in the way. Loud noise. Come on. There we go. I'm just going to leave you here then. All right. So weights. So I also mentioned about weights. So the weights are kind of like essentially how much each little point in here matters to the next neuron. And so usually you'll see like arrows in here. Sometimes like you saw in when we showed implementation, like visualization of like these neural networks, it was like different like brightnesses and like thicknesses of those arrows. Essentially that represents like how much like how big that number should be, whether positive or negative. I think if you watch the 3 Blue 1 Brown playlist video, you would see that he has different colors. I'm assuming he like actually changed the values on there, but like the different thicknesses and brightnesses are supposed to represent weights as well. And then basically it's just kind of like saying like, how much does this actually matter? I kind of wrote this right here, is that you can think of the weights as of the hidden layers, telling us how much these linear separations should be combined. So you're like, what does that mean? Like linear separations. You can kind of think is that each one of these parts is saying like, how can we draw a line through the data points to separate them out? And it says, how much does this layer actually matter? So I want to show this a little bit later. I almost, we'll come back to this. So someone remind me about linear separations when we see the TensorFlow, like the thing we saw yesterday with like training the model with the different diagrams, you know what I'm talking about? Yeah, so for the record, I'll show you this guy right here, right? Just remind me linear separations, okay? So, all right, so anyway, that's what you can think of weights. Basically, how much does each neuron or how much do these different separations, or you can almost think of like latent features really matter, okay? And then we have activation functions. So we'll discuss this in a second, but activation functions basically say, okay, all of these values come together to form this one neuron. So you can think of it like this guy right here, like this neuron right here, we will call it like, well, what is that? Number of people that walk by, something, whatever feature this is, right, that's going to be created from this neuron, comes from all three of these things. You can think of activation of saying, okay, these have different weights that come in through here and they get summed up together and they create this new value. How big does this value have to be for it to really matter for it to be passed on to the next part? So maybe, for example, if this value is really, really small, it shouldn't really be considered that important. And so it should just die off. But maybe there's something like, oh, if it's closer to 0, for example, like it's actually like, this is actually really good. This is a really good value or something. So that's what the activation function is, kind of like the gatekeeper of like this value passed in here and how much this neuron matters before it gets passed on with its weights. This is kind of important because it helps with training. So it basically means that it won't take forever, but also it's here to model a little bit of like activating neurons. Again, I'm no neurobiologist, but from my understanding is that you might have multiple neurons come in onto one like neuron, and they will only fire if a certain amount of neurons actually activate it. So like you can think of like, oh, well, of the 5 neurons, maybe there's 2 neurons that fire. It's like, well, then it shouldn't fire the next neuron. It's like going to wait until there's 3 neurons or something like that.
And these
Mhm.
activation, the activation functions actually act like an on-off switch, don't they? They have a
Yeah,
threshold, and they're going to be either on or off.
yeah. It's a little more it's a little more complex than that, but basically it's an on and off switch, like you said, Alvaro. Usually they fluctuate between 0 and 1, but there's also a little bit of leakiness where like it might be like 0.9, you know, and that's important to talk about. And we can talk more about like different activation functions that do that. Yeah, Jessica.
Something Alvaro mentioned that I was curious about too, like, is there a threshold? Like, and does the neural network just choose the threshold on its own type thing?
Yeah, that's a good point. So the activation function is going to be built in. So we're going to say this is the function. And so we'll see this in a second. This is kind of abstract right now, but we'll see it very like really clear. But basically there's a function we define. For example, there's the sigmoid function, the hyperbolic tangent function, the ReLU unit or ReLU function. That basically it's like defined. It's like, oh wait, if you put this value in, this output will come out. And what we do is that we keep that steady, the activation function, but we allow the neural network to adjust the weights. And so what will happen is that the idea is the neural network will learn, okay, like this activation function needs at least this value for it to be on. So it's like, well, I want this to be on. So I'm saying want, but you guys get the point. It will increase the weight, for example, to try to make it a bigger value so it does get activated. So in ways, the only thing that the neural network can really change are the weights, if that makes sense. The weights and the biases, which, you know, the bias is just basically a weight that doesn't go to any one parameter. Does that make some sense?
Yeah, it
Okay.
does. And so, for example, like with a sigmoid function, you know, we have like 0 and 1. And so like how we see in logistic regression, there's like a threshold somewhere where it'll give it like a 0 or a 1. So I was just wondering, like, yeah, is there some hidden threshold there?
Yeah, so not so much. I
Okay.
think what you're saying, like logistic regression, we say, oh, there's a threshold, and then we say positive or negatives. We use the fact that the sigmoid's going to have, or whatever function, a value between 0 and 1, and that's the value that's going to get passed on to the next layer. So you can kind of imagine is that like with this like hidden layer, like let's say this hidden layer, these values are going to be like, you know, from the summation, the linear combination, this is going to be like a 7, this is going to be like an 8, it's going to be like a -2 or whatever. And maybe this will only get activated, like, you know, whatever activation function we use, like, okay, if it's 8, it's just going to say 1, and basically it doesn't pass on this 1. And basically it's to kind of like even out like the fact that like we don't want this neuron to overtake everything. Like if this neuron's like 100, it just means it should be on. But like maybe these neurons only go up to like 3 because of just the way the linear combination works for the weights. And so you wouldn't want this neuron to do all the heavy lifting of everything determining it. So basically the activation function kind of like says, hey, just relax a little bit. Yo, I get you want to get activated, but we'll just kind of like put you closer to 1. You don't need to be 100, just 1, so we can make everything fair and even for the rest of the neurons. Hopefully that kind of makes a little more sense.
Yeah, and so it's like everything's 0 to 1, right, with like the sigmoid function. And so if it comes out like 0.7, there's some threshold that says like, okay, 0.7 is going to be a yes, like that's going to be 1, is what I was
Kind
wondering.
of. It's more like 0.7 gets passed on to the next, like
Okay.
0.7 will get passed on over to the next one multiplied by some weight.
Gotcha. Well, that's what you're saying about like weights. Or no? Yeah.
Yeah,
Okay.
it kind of regulates the what the output is.
Yeah, you can think of it more like a built-in
get that.
gatekeeper to the neural network. Like
Okay.
you create the structure and like that's the activation function now. It's not going to change.
Okay, that makes sense. Thanks.
Okay, no problem. Yeah. The biggest thing, if you remember, is that the only thing it can really change is the weights. Like that's really what a neural network can do, which is really impressive when you think about like all it can do is just adjust these weights, and somehow it's able to figure out what the best weights are. So it's pretty cool. All right, so that's activation functions. Other hyperparameters. So hyperparameters are basically the parameters that will be modified to enhance the learning. We call it learning for a neural network, right? Or learning for a machine learning algorithm. The idea there is that these are the things that help it arrive to the correct answer, you know, over iteration. But that iteration is going to be an epoch, right? So of forward propagation and backward propagation, one epoch. And that iteration over and over again is to say, how much does it learn over each epoch? Okay, so some things we can do are learning rate, we call it alpha, just basically how big of a step we take in gradient descent, which is going to be part of the actual learning process in neural networks. So essentially what we're going to do with a neural network is all it's trying to do is trying to minimize this cost function, this loss function, basically saying how close to the answer can it get? And it'll keep modifying until it can get closer and closer and closer. There's some tricks too about that, because if you guys learned back in gradient descent can be really tricky too, because you get stuck in a little valley, right? Like you might not be able to hop out of it, or you kind of miss the answer. Like you can kind of think of like a ball rolling down a hill for gradient descent. And if you have this little tiny divot, the ball will kind of hang out here in this divot, but maybe there's even a better divot down here, but it'll never find that unless it has enough momentum to kind of power over. So that's kind of like the idea for learning rate, is that how big of a step do you take to make sure you find the correct like valley, the lowest point, right? And the lowest point means the most correct answer. Okay. Number of epochs. Oh, question. Yeah.
No, I mean, for that problem, that's also why you have batch gradient descent, right? Batch gradient descent and stochastic gradient descent.
Yeah, we'll talk about that too for optimization. Right. Like different, like there's different techniques you can do to help do steps. For example, I'll just kind of quickly say, when you take a step in like with alpha, like how big of a step? Well, if you imagine like you're going down a mountain, you might take some really big steps to kind of like get you there faster. But then once you get down to the close to the bottom where it's relatively flat, or like pretty close to like the minimum, you might take little small steps to make sure you don't overstep like the smallest point. And so you can adjust the learning rate. That's kind of stuff you can do. You can change momentum. You can change like how many, Vera mentioned this batch. So a batch is basically like how many data points we feed into the neural network for it to learn in one session. So one thing we could do is feed in all of the points at once, like the full data points we're using for training, feed it through the neural network, and then figure out with backpropagation how the neural network should be adjusted for all of those points at once, which you can do, like you totally can, but it might take a long time because you can imagine trying to figure out what the different dials you should do for all the data points at once can take a long time to figure out, basically because of the derivative. So one thing you can do is do like mini batches, like where you take like, maybe a very small segment of the data points that you're doing for training and feed it through once, adjust the weights, and then feed the next batch again and adjust the weights. And that tends to effectively work faster. It means that each step is not going to be super accurate, but it turns out in the collective, it tends to actually approach the solution very quickly. Question. Mm-hmm.
Do they get averaged in the end?
Actually, it turns out because you're taking steps down, at the end is basically you're done. Like you don't even have to average anything because essentially what you're doing is, how do I say this? I'm going to go back a little bit gradient descent because I think it's kind of useful. Well, okay, tell you what, I will come back to this a little bit, but I will kind of say batch is kind of like considering like if you're in a mountain. I don't know, did I talk about gradient descent with you guys before I went on leave? Yeah, I did. Okay. Did I mention, do you guys saw Bird Box? Has anyone seen that movie on Netflix with I forget the actress's name, but she has like the blindfold and like because they all can't see because there's some. It was like a year or two ago. No one knows what I'm talking about.
Yeah, no, I saw it with.
Okay, I see some.
Yeah, what's her name?
Sandra Bullock, right? Is that
Sandra Bullock? Yeah.
okay? Anyway, Bird Box. If you haven't seen it, I don't know. You can watch it. It was fine. But the premise of the movie is like they have to wear these blindfolds. So imagine if you're blindfolded on top of a mountain and your goal is to like find this like the lowest point. You can kind of imagine like if you're standing, what you would want to do is like, okay, you feel around the hill, right? And see which is the lowest point and then take a step in that direction. That's kind of like what we're doing when we do gradient descent. Mini batch, or like taking a batch of it instead of all of the data at once and then seeing what direction we should go, is kind of like, it's not exactly, but it's kind of like only looking at a portion. Instead of looking 360 to see what's like, what direction should we go, you only take like, maybe like a random segment of like what you're looking at. It's like, oh, I'm gonna look in like, thinking like 0 to 60 degrees from like where you're standing and only look at there. What's the lowest point here? I'm gonna take a step in that way. But maybe if you turned 180 degrees, there was even a lower point, so you'd miss that point. But it turns out if we do enough mini batches, we'll eventually kind of like find the lowest point. In theory, sometimes it doesn't quite work out.
Would a good analogy be like instead of one person trying to find that lower point, you have a few people all in different regions looking for that point? And
kind of.
And somebody's going to find that lower point.
Yeah, this is where the analogy kind of breaks down because it's kind of like it is still one step that's going through there, and so it's not so much like different people. Like Jessica was kind of saying, "Oh, do you average them out?" It's not so much that different people are doing it and then we average it out. It's kind of like you're only taking a certain amount of information, and so it looks as if this is the lowest point. But if you considered all the information, you would actually say, "Oh, that's not actually the lowest point. The lowest point is this direction." That's kind of what's going on in mini batch stochastic gradient descent.
And then it finds, thank you. So then out of all the batches, it finds like the lowest out of all the batches. Okay.
No, sorry, that's the wrong way to say it. So a batch is kind of like you take a step down and then you have a new batch from where you are and then move from there. It's kind of like the time series with random walk. It's like you're still where you are. Like you don't go back to start. You kind of like keep progressing forward. So you get a new set of information to proceed forward.
So then is there a limit where like if it reaches a small enough like slope, then it's gonna stop before it even keeps going on to more batches?
That's right. Yeah, and this is good you're thinking about this because that's exactly what we're going to talk about in optimizing neural networks is exactly that. It's like, okay, like how would you do this? Like, okay, like if you reach a certain point, you would stop, it's like, okay, like it's low enough and you would kind of maybe consider a bigger batch or maybe even just like say, okay, this is good enough. Maybe you overstep it, maybe you do some other things. That's kind of what optimization is really they're trying to do. So that's good.
Cool, thanks.
Yeah, no problem. And I like these questions too, because I think you'll see them kind of like, these are questions you kind of ask yourself and then we'll kind of hopefully like answer them as we go through this, these study groups. Cool. And then I'll just mention last hyperparameter, number of epochs. right? Just how far you're going to repeat the process. So ideally, if you can probably guess that the more epochs you have, the more likely you'll get closer to a better answer. There is an issue with this though. If you do too many epochs, you might start overfitting, thinking you're more confident in your training data, where in reality you should have stopped early on, or you wasted your time. You say, I'm going to do 1,000 epochs where it only took 100. And it's like, oh, you just wasted like a whole bunch of time, basically get like no benefit or very little benefit. Okay. But we'll talk more about this for sure, like in the future. Okay. Maybe today, maybe partially today, but we'll see. Probably not, just how much time we have. We'll see. All right, just make sure I'm reading this. This is structure. Yeah, basically you can think of hyperparameters like that structure of the neural network. I'm saying how it's going to learn from this point. Okay. Okay. So let's talk about like training it. I'm going to go through this really quickly. Just give me a thumbs up when we did either reading from curriculum or watching the YouTube playlist from Threadgill and Brown. How are we feeling about backpropagation? Thumbs up, thumbs sideways, thumbs down. Okay, see some thumbs up, see some thumbs sideways, that's okay. All right, so the main thing you have to know about backpropagation is don't stress out too much about implementing it unless you're doing research, essentially. And by research, I mean researching how to do machine learning more efficiently. Not how to use a machine learning algorithm for your problem, more like how do you do better machine learning. It helps to understand what's going on in here, but like if I'm gonna summarize this in like, I'll give myself 30 seconds to summarize backpropagation. Backpropagation is saying, hey, how do we adjust the weights? How do we tune these weights based on the data we fed it through using the chain rule and gradient descent? That's backpropagation. That's kind of it. There's not, like, the way we do it is going to be much more mathematical. Like you can see this is actually taken directly from that playlist, one of the videos from Threadgill and Brown. And basically, I think he talks about this in the video, if I remember this right, is that he says this cost function C0 is basically how good or bad your answer is, right? How far away the answer you are from it. And basically the backpropagation tries to optimize for saying, if I move the weight this much, does the cost function move a lot, right? And so the idea there is that it tries to figure out what's the best way to move it, but it does this for all of the data points in the batch. So instead of doing just for one, it's doing for all of these ones and averaging it out. Well, I say averaging it out, but basically considering all of those data points. And so it knows how much to move it by. And so the cost function will always, your loss will always be, will always be smaller than it was previously. Okay, cool. Yeah, just to kind of go through a little bit what we have here, the backpropagation algorithm takes the idea of optimally adjusting the parameters, weights to get a better result. That's really what that is. So we feed it forward and basically say, all right, solidify this neural network, push all the data through there with whatever weights it was previously assigned to, so maybe from a previous epoch, see what the loss is, and then use the backpropagation to basically tune the weights as we kind of go backwards through the neural network. Okay, all right. Yeah, and you'll see the cost function J, right? So you'll see classically J as being cost function. Gradient descent, cool. Does that kind of answer questions for, I mean, does anyone have like follow-up questions on backpropagation specifically? Like we could dig into the math, but I just don't think it's necessarily the best use of time. We can do it in the future for sure, but any questions or comments on backpropagation? All right, cool. Oh, Jessica, go ahead.
I was just gonna say, I don't know if anyone does have any questions or not, but what really helped me was seeing the equations all together, because then I could just see like, okay, this is gonna change the weights in like here and here, and that made it really easy for me to conceptualize. So if anyone out there, you know, seems like
That's
everyone
good.
gets it.
And was that from the curriculum that you
questions.
saw? Was that from the curriculum that you saw?
It
or
was
from
in the video. It may
Yeah.
also be in the curriculum, but just seeing like the equations together, it made it easier to understand. That's why.
Yeah, I'm comfortable with the chain rule, so it's kind of easy.
Yeah, once you have the chain rule, it's like, oh, it's just basically these together. Like there's a bunch of like little notation stuff like this, and it's kind of like in physics we used to talk about like it's just the index tracking and figuring out like what thing am I looking at a time. But in the end, it's like, oh, we're just basically just moving backwards and having those equations all together. You can see, oh, that's why we have the derivative of this one, this one, and this one. Which again, if you look carefully, it's like, oh, that's really just gradient descent. That's all we're really doing. Cool. All right. All right. So I'll move on a little bit. So I'll kind of mention this is where like section 41 is like, oh, deep learning. Deep learning, we got more neurons in the neural network. Basically, we have more layers in there. And basically it means a little bit more complicated, but in reality, it doesn't really change much from like how we would approach solving a neural network. So sometimes you'll call it like deep learning, deep neural networks. You'll see it as multi-layer perceptron networks, or MLP sometimes it's referred to. They're all the same thing. And it turns out these are really powerful because basically you have features on features. Like they're not really features, but I call them like latent features, doing other latent features, doing other latent features. And like this is like got 2 hidden layers, but some of the like most advanced stuff are like literally like hundreds of layers like deep. Like there's many, many moving parts in there. ImageNet is one of those examples that can do object detection and stuff like this. But what's really cool is once you have it trained, which can take a long, long time because it's super complicated, assuming that you don't have it overfit, you can actually just apply this, and it's actually relatively quick for neural networks to put in inputs, and just like basically you're just multiplying numbers together and then seeing what the output is. So that's kind of like a really cool thing about neural networks. However, it can be kind of big. Your model can be large because you have like different layers and different numbers in there. But for the most part, a lot of these things are optimized to actually feed forward. Feed forward is almost like no time at all. It's usually the backwards propagation. A caveat to that, neural networks like this I'm showing you, relatively quick feed forward, and actually implementing recurrent neural networks, sequence to sequence models, those are not, those aren't necessarily very fast. And there's a reason for that. Basically, it depends on the previous result. So you have to wait for the previous result to go through and then get the next result and then go through. So just kind of know that not all neural networks are super fast. It's just that these ones are relatively fast for what results you get. Okay. Cool. All right. Cool. So I'm going to kind of, and that's deep learning, right? So not too hard. Let's see, I'm just gonna, I said, why do we not complex all the time? Like I said, basically is that like it's more complicated. So it's more complicated. When you hear that, it's in machine learning, it's like it's more complicated, think overfitting, right? So if it's more complicated, it means you can accidentally find patterns that don't actually exist. So we increase our chance of overfitting. There's some ways we can optimize for that and avoid that. We'll talk about that later. And then just more parameters mean more computation. So computation time meaning that like it takes a while for it to train. So if anyone's heard people talk about machine learning neural networks and stuff like this using GPUs or TPUs, GPUs are graphics processing unit, think graphics cards. So classically they've been used for games and like, you know, computers and like figuring out like different like little pixels and like how they should move and stuff like that. Turns out they're really good at doing matrix multiplication. So that's why they're used for training these things. But literally like some of these neural networks, I mean, it's hard to say something right now because like I would say, oh, I trained a neural network and it took me like 3 hours. Well, depending on like what GPU you were using, what system, it might actually take like now it's like, oh, that took like 30 minutes. Neural networks existed before, and it would literally take days to do a very simple one that you can do now do like maybe less than an hour. But there are neural networks that literally train for days as well. So basically the more complicated it is, the more computation you need because we have all these little weights for adjusting. Okay, cool. All right, sound pretty good? Any questions about structure, parts of the neural network? I think that's pretty exhaustive at this point. Biggest thing that I just probably don't have, sometimes you'll see weights drawn on like these arrows or the arrows representing the thickness and stuff. Just think of whenever you see this neuron, this is a number. And then whenever you see an arrow go to another one, this is multiplied. This number is multiplied by whatever the weight is here to get this number, which is going to be like whatever this number is multiplied plus whatever this number is after multiplied, plus this number multiplied, and you get a new number. Okay, cool. All right, so let me just go back a little bit to activation functions, which I believe I have right here. So this is important to kind of like talk about like what is going on here. I'm gonna run this guy. So what is an activation function? We kind of talked a lot about this. Basically, it's just like almost like the gatekeeper of saying how much, you know, the next value should be passed off to. So like I mentioned, like if you had like 100 for that neuron, you don't want to pass 100 over because maybe everything else is on the scale of like 1 or 2. And so the problem is that neuron now would overpower everything and it would be difficult to train that properly. So an activation function basically limits how much it should be activated. It also works in the negative direction or close to 0 direction. Okay, so there's some commonly used ones. Sigmoid, give me a thumbs up if you guys in the curriculum or wherever saw sigmoid, right? So I will tell you right now, it's cool to know how it works. don't use sigmoid in like the real world. Well, basically, it's kind of shown that it does fine, but it doesn't do great. Like it's actually not really the best way to do it. Basically, the range, basically its output will be between 0 and 1. So we actually use like logistics regression, right? I think Jessica mentioned about logistic. And you can see here, it's a little small, but 1 plus e to the minus x. So whatever x is going to be the value you put in there. And basically, no matter how big x is, however small it is, it's always going to be between 0 and 1. Okay, and that's kind of the idea of a sigmoid is very close to how neurons work. And that's kind of like the idea of where it started off with. We found some other ways to optimize this and train faster. So some advantages, it's relatively intuitive at classifications. So basically it's like you're either this thing or not. So we'll still use sigmoid, not for training, but sigmoid for classification. So instead of having one neuron at the very end on the output layer, you might have multiple neurons each for each class that you're going to identify with for classification. And sigmoid will basically be that threshold, kind of like logistic regression. So it's really great for classification. It's commonly used, so you'll see it a lot in people talking about, but in reality, it's not really used too much in industry anymore. Might still be, but it's just not that great. It's not as efficient in training. It means that you have to train longer and more complicated. Basically, things tend to survive that shouldn't be there. Also, vanishing gradient problem. Anyone heard this already in the curriculum, vanishing gradient problem? Okay. Main thing about vanishing gradient, I see some nods, see some head shakes. Main thing about vanishing gradient problem is the gradient's too small, it'll tend to go down to 0. And the gradient, if you think about it, like kind of like saying like your slope, right? Like how steep is it? And you want the slope to figure out the smallest point. If the gradient's too small, what's going to happen with certain functions like the sigmoid function, it'll disappear. And so basically you lose that information. And so it's not really that great for that issue. To show you a little bit, here's a little visualization in code. So the sigmoid function is in actual red, so look at logistic regression. So basically, if you're like very negative, it's close to 0. If you're close to 0, it's like it's actually 0.5. And as we get closer and closer to more positive, right, we have 1. So this is kind of like the output on the y-axis. I also put the derivative here, and you can see here is that the derivative right here is like, where do we move? Like you can think of the derivative of being like, how much should we move the weight, right? How much we should, and you can see here is that you will move it the most when it's close to 0, like on the side, and you'll move it in the positive direction or negative direction. If it's already like way negative over here and it's like doing well, there's no reason to move very much. Like you think about that, right? Like why would we move it? It's barely doing anything different. So the weights kind of stay the same once it's basically really negative, really positive. So that's kind of the idea there. Okay, makes sense? Cool. All right, so let's talk about, now we see one activation function, now it's just different functions of what it looks like. So we have hyperbolic tangent, or tanh, ranges from -1 to 1. Doesn't really matter too much about the range, just that usually activation functions, we want them relatively small in general, because then it doesn't overpower anything. That's kind of the idea. So you'll see a lot of these activation functions. There is an exception, which we'll talk about with later. But tanh, which this is hyperbolic tangent. For the record, hyperbolic tangent almost has nothing to do with actual tangent. It's just that the pattern is very similar to tangent, sine, and cosine. So we have hyperbolic sine, hyperbolic tangent, hyperbolic cosine. But basically, this is the equation. Don't worry about it. Like you don't have to worry about like memorizing that equation for any reason. Some advantages: it's more efficient than sigmoid. It's got steeper gradients, so basically means that if you need to move the weight, it won't take as long for you to keep like adjusting. It will do like one big step because the gradient is much steeper. Okay. Disadvantages: it still has an issue with the vanishing gradient problem, which again is kind of a big deal when basically we want to tease out a little extra information, but it's not there. So yeah. Just to kind of visualize it, you can see it's very similar to the sigmoid function. So you can see this is a sigmoid right here. This is, here, let me just move this like this. There you go. So sigmoid right here, you can see that, and then hyperbolic is in this red right here. So you can see besides going from -1 to 1, you can see it's much steeper, right? So we're gonna have a quicker convergence on the weights, and you can see in the blue here, which is a derivative, you can see that's a kind of steeper slope, right? Meaning that like, well, I shouldn't say steeper slope, but you can see like the values are much higher when they're very close to the 0 part. So you'll move very quickly versus like waiting for it to slowly iterate over and over again for you to adjust those weights. Okay, cool. All right, so let's move on then to the next one. So let's talk about ReLU. So ReLU, or rectified linear unit, That's what it stands for, rectified linear unit, ranges from 0 to infinity, which is much, infinity is a little bit bigger than 1, as you might have guessed. And so it's actually a really simple function. Basically, if x is less than 0, it's 0. If x is greater than 0, it's x. Like, it's a really simple function, which means it's actually like really easy to like put the calculation in there. In fact, most TPUs now actually have ReLU optimizations in there because it's like, oh, we can just do this in the hardware level kind of stuff. So kind of something to know about is that hardware also does play a role in like how quickly you can train things. So you'll hear people talk about TPUs, which are a tensor processing unit versus a GPU. TPUs, I think, I could be wrong, but I think I know they're talked a lot by Google. I think Google, I want to say Google developed them, but maybe I'm wrong. Is that?
Yeah, it's Google. It's really a GPU. It's just their verbiage. It's just their their branding.
Yeah. It's optimized for that specific tensor multiplication. And it turns out TPUs, and certain TPUs can actually use ReLU pretty well. Kind of the same way like Bitcoin, there's some Bitcoin like processing, like they used to use GPUs, which is more general. And now there's some that are specific to like cryptocurrency, like basically figure out hashes and stuff. But that's not super important for us for today. We can specify a more positive activation, which, oh, go ahead, Jessica. Yeah.
I was just going to say, wait, what does the G stand for in GPU?
Graphics.
Okay.
Graphical. One of those two.
Okay.
It's graphics. Basically, originally GPUs were meant for just putting graphics, like pixels on the computer. Like if you imagine a video game, like it's like, oh, the person turns this direction. It's like, well, what color should that single pixel be when they turn? Well, you can do a model basically in that. And part of that's actually matrix multiplication, which is why, even though it's meant for graphics, we can use it to do matrix multiplication because it's more efficient than, what's it called? CPUs, computational processing unit. They also can be parallelized really well. So there's basically all of like GPUs are parallelized on purpose, like all the different cores. So anyway, we can talk a whole bunch about that too. But anyway, cool, saw thumbs up. So specify a more positive action, this activation, this kind of makes sense is that if you're going in a good direction, you kind of want to like keep encouraging it to go in that direction. Like that's the kind of the idea of like having a more positive activation. So in practice, ReLUs actually tend to do much better than sigmoid and other activation functions. I'm sure there's research to show that there's certain problems and stuff like that. I personally don't know what the difference is. So my suggestion is that in practice, probably use ReLU versus like sigmoid. Okay. Disadvantages, the 0 value, it's still longer to train. So if you look at the actual description, and this looks complicated, like you probably look at this like, oh, this looks more complicated, Victor, but we can actually logically talk about this, like when it's optimized and compiled, it turns out this is a very easy thing for a computer to understand. But in the red here is the ReLU itself. So you can see basically it's just a straight line. So this is the linear part. And then you see right here, it's a 0. And so what happens is that if you are negative right here, you kind of think like, yeah, we should probably turn that weight down, right? It's way too negative. It's in the opposite direction of what we want. The problem is it doesn't know what direction to go. It's just 0. Like negative like 5,000 and negative 2.5 look the same to a ReLU. So it doesn't really know how much it should adjust. So that's kind of the reason why like say, okay, like it's not really great when it's as these values get to 0, it takes longer to train in that way. But in practice, it actually does pretty well. So a solution to this is called the leaky ReLU, which, and there's a whole bunch, I will tell you right now, there's other variations of ReLU, which I'm not going to get into, but just know they're kind of like in the same vein of leaky ReLU. So idea here, it goes from negative infinity to infinity. And basically there's this little c right here, this negative c, that instead of going to 0, it's just going to make it more negative. And it's usually a small value. It's kind of like some proportion of this negative value. So advantages, basically everything with ReLU, it helps with training speed because we're now getting rid of that negative part. Some disadvantages, it's a little bit more compute time now. It's not as easy to put this into a hardware unit easily to say, oh, it's going to be negative in this way, but it's not too bad. There's other parts like, oh my gosh, why can't I think of it? The other way you can do like a leaky ReLU, well, I'll show you a leaky ReLU first. You see that? There's ReLU, and then basically this is a leaky ReLU where it's basically slightly more, or a little less negative than what the original value is. And the idea there is basically it's still learning to, oh, how I should optimize this. So you can see the derivative is a little small, but it's still there. It's not completely 0, which is kind of good. So now I can distinguish between very negative values and slightly negative values. There are kind of like difference of this. Like you can see things where basically this is an exponential, like a negative exponentials, and you kind of see those kind of values. But the idea there is like there's optimization and stuff. And my suggestion is like, what should you use? Like what activation function should you use? Probably ReLU. That's probably the one you should at least go for. You can then try more exotic ones and look at what the current research shows. Okay, cool. All right, cool on activation functions. All right, cool. Look at that. We got all the way through it. Sweet. So, all right, we have 5 minutes left for Keras implementation. So, tell you what, I'm going to go another 10 to 15 minutes longer. Are you guys cool with that? All right. If you have to go, it is recorded. So if you have to, you can watch this part. But we're going to start going into Keras implementation, and we'll kind of see like, okay, how do we actually use this? And then next time we'll talk about optimizations and stuff like this. Okay. Oh, before I finish off this, I should have done this. Someone was supposed to remind me about linear separation, right? So I kind of mentioned this very quickly, like at some point, linear separations for weights, like it's like, okay, we have this linear separation, how much does linear separation matter? So going back to like this neural network, you guys remember seeing this like last time, right? With this cool looking thing. All right, so I'm gonna go to, I'm gonna just use this guy. And so if I run this real quick, you can see different stuff. This right here, you can think of this neuron is how much that should create a linear separation. And says this weight then from here to here is saying how much does this linear separation matter to the next neuron. So you can kind of see is that like this neuron right here relies on 1, 2, 3, 4 different separations, and that the values being fed into here tell it how much proportion of these linear separations should be combined. So you can see, for example, it looks like the weight going from here to here is like 1.1. This one's minus 1.3. So it's kind of like, you can imagine flipped over, and then minus 1.2. And you can see is that if you look at this like little diagram, you guys see that little diagram, like the blue and orange in here, you can see it very closely resembles this one. That's because most of the value comes from this one linear separation. And then it combines with this one. In this case, it's negative, so it's flipping it over. And you can see this one right here, I even forgot about this fourth one. It's completely flipped over, which is almost like, you can see it's very close to the opposite of this one. See that difference? And you can see it's almost like 0. It's close to 0, minus 0.25. So basically this matters very little to this activation right here, or this neuron, okay? And that's what I meant by saying, oh, it's like how much linear separation, or each of these linear separations, how much does this matter to the next neuron over? And that's kind of what the weights are doing. Does that make sense to people? Cool. If you see this more like complicated, like this, and you see this now, what you'll see is that these will get more complex and such. I actually think this might not be the best example of this, but you would see more complex patterns. There we go. Took a while for it to figure things out. But you can see here is that now like this is very simple, and then it gets more complicated where now these are combinations of combinations of combinations of combinations. So that's what I meant by linear separation. Okay, cool. All right. That was the quick sidetrack. Now back to Keras implementation. All right, cool. So Keras implementation, this is just how we're going to code up our neural network. I'll run this through this relatively quickly, but I'll kind of explain the code as we go through. TensorFlow, we're going to use TensorFlow in the cohort. I think your learn environment should be equipped with like 1.14 TensorFlow. Just know that there is now TensorFlow 2.0. So if you do look for code or look for documentation on TensorFlow, just notice that that might be a 2.0 feature. If you want to, if it doesn't hurt, you can update TensorFlow or create a new environment with 2.0. I would suggest it just because like now that's kind of like the more common thing. There's no backwards like breaking. Like TensorFlow 2.0 for the most part doesnn't break much of TensorFlow 1.0. There's some caveats, but there are probably things, to be honest, that when you're first learning, you're not even going to notice at all. Versus Python 3 and Python 2, don't ever use Python 2 again unless someone has a gun to your head, I guess, and you have to use it. And when I say gun to your head, I mean because they're paying you. All right, so TensorFlow, Keras. So Keras is actually its own library, but it's actually built into TensorFlow, which is pretty awesome. And then we have first with Pandas, NumPy, Matplotlib, so we can do some stuff, and Random Seed, just so we can have some consistency in our life. All right. And then Keras has some extra like libraries within it, so models and layers and optimizers. I'm just importing it like this. You'll see people import different ways for Keras and stuff. I'd say if you see something cool, like look at their code and see how they're importing it and see like what they're doing. Keras can be used from different places. There's different optimizers that you can use, and they'll basically have Keras, and some people will import Keras, they'll import Keras as K, and then they can just use the K part and just knowing it's gonna look like Keras and stuff like that. So it's kind of cool. You'll see people use that a lot. So I'm just gonna run that, and just know this using TensorFlow backend is because it's using TensorFlow up here. That's why it's saying that thing. Okay. All right. So let's actually check out this code. Ooh, super intimidating. It's not that scary because basically all we're doing is the stuff that we've done before. I'm getting some data, the iris data set. So remember, iris is the flower petals and stuff like that, different size length. I've shown this at least a couple times before in the past. We're doing model selection where we basically do a train test split. So this is the only function I really use. And we remember train test split, right? Yeah, we should. Don't you get caught without ever doing a train test split, right? So making sure we have our validation, our train, and then our testing at the very end, right? So we're using that. And then I don't know if you guys have seen this. This is more for pipelines. Pre-processing from sklearn, one hot encoder, standard scalar. Have you seen this before? Okay, cool. I see that. That's awesome. So basically, I'm just importing these libraries, right? Or more specifically, these functions. I'm loading the data set, so I don't have to get my own data set because I'm lazy. I'm getting X, so X is basically all the features. Y is the target. I think there's 3 different classifications for iris, and that's going to be 0, 1, or 2. I think that's right. And then just getting the names so we can actually know what their names. It doesn't really matter. We just care about what the classification is. Feature names, just know what the features are. So really the thing that matters is X and Y, okay? And then we're going to do one hot encoding. We're encoding basically our Y. So this way we can make sure that the encoding is going to be for, sorry, not encoding, but like the data actually shows the target as 0, 1, or 2. But remember, one hot encoding, what we really want to say, oh, is it, for example, you guys know what I'm talking about when I say one hot encoding, right? Let me know if you guys remember that. Okay, and this is where it's super useful, like neural networks, because remember, like 0 is going to be like 0, or does it say 1, 0, 0, and then 1 is going to be 0, 1, 0, right? And then like 2 would be 0, 0, 1. All right. So the idea here is that you can think of each of these as vectors. Well, this can just be our output layer. Our output layer will basically have 3 neurons, and we're just going to look at basically what's the largest value in each of these placeholders. And so whatever the largest value is, we'll say, oh, it's that class. So for example, if I have like, oh, like this is my y hat, and the y hat vector from the neural output, neural network output would be like 0.2 minus 0.3, and then like 0.98, something like that. I'm making these numbers. These numbers wouldn't actually work. But like you just see something like this, you say, oh, it must be class number 2 because that's the most common one, or that's the largest value. Okay, make sense? Cool. All right. So important to know that you have to one hot encode. Don't ever not one hot encode for your classification, for at least neural networks. All right, scalar, I'm just making it so it's a little bit easier. We've seen this before, X-string split. Cutoff, I'm just making it so I don't have to, I have my train and test. So remember, what do I do with tests? I don't touch it until the very end, right? Like, make sure I don't look at that. I want to keep that separate because that's how I keep myself honest, right? So that's kind of the idea we go through. And then, yeah, so I'm just keeping 90%. So I'm training on 90% of it. Okay, cool, cool. All right, so I got valid, my train. So nothing too special yet for at least neural networks. So from Keras, we actually have our models. We can import sequential. And this basically, sequential is kind of like saying a sequence of being like, oh, we have our first layer, our second layer, our third layer. That's what you mean sequential. There are more advanced things where we can like skip over layers and stuff like this, but we're not doing that with this neural network. But you could do like really fancy stuff like that, which is kind of cool, but we don't need that. So our model is going to start off with sequential. So note that I classically just call it model equals sequential. Easy enough. And it's giving me a warning knowing that whatever version I have, I'm going to ignore it. It's deprecated. It'll still work. Okay. This is where like if you get warnings, like look into it, but don't like freak out, right? So that's what I'm doing right now. So the actual network, we can decide how many layers and nodes. So we're going to start with a very simple one. So basically we're just going to have 30 units. That's going to basically be a neural network. It's going to input, so the input dim right here, we start off with 4 features. So if I showed you like the shape of X, X would be 4 with, or however many rows, comma 4. So basically the input dimension is just, there's 4 different features. So I'm inputting a 4, And then it's going to go to this neural network, in this case, units of 30. I don't know why I put 30. I'll keep it there. But basically, you can imagine like if I had a neural network, we have like the 4 inputs, and then the next layer would have 30 different neurons all connected to those inputs. And then the layer after that is going to be 3 units. And has anyone got any idea why I do 3 units at the end on this output layer?
You have 3 classes.
You have 3 classes, right? So that's the reason why we have this units 3, right? So this is what we want. We want to have those 3 outputs. And then note this activation is softmax. Basically, that's going to make it so it's kind of like sigmoid. It's going to make it so it's either 0, like ranges from basically 0 and 1. I think -1 to 0 or -1 to 1. Don't remember now. Someone remembers. 0 to 1. Thank you, Alvaro. Caught in my own head. Yeah, so basically we'll have these values that range so we can do the argmax. So I think I did this wrong then. This should, like when I showed you the little one-hot encoding,
I think it just it takes all of the outputs and then normalizes them. So
That's
that
right.
you get
Yes.
0 to 1.
That's right. Perfect. Okay, so let's run this guy, or we now made this model, gives me a warning that we're just gonna ignore. And so this model doesn't do anything. We just basically define the structure and said, hey, we wanna make this neural network with this structure, like, you ready for it? And it's like, okay, cool. So this model.compile, basically, we're gonna go through all this stuff next time with like what these different things are. But basically, the model says, all right, you're gonna compile the model and get it into a form that the computer can easily digest and use like the C code in there to run really quickly. We're gonna use this this keras.losses.categorical cross entropy. That's just gonna tell you how bad or good your model is. So this is how it determines the loss function, hence the loss right here. We're doing categorical cross entropy because we're looking at categories and we're not doing anything too fancy. Optimizers, don't worry about this too much right now. There's some things we can do to basically make it optimized. We'll talk about this next time. And then metrics, we're just gonna measure the accuracy so we can see this. This will not change how the model compiles or runs. It's just nice things we can see as the model is being trained. Okay, sound pretty good? Cool. All right, so it's nice we can actually do model.summary and it'll actually show us like the different layers. So dense 1, dense 2. We could have actually even named the layers too, which is really useful when you have bigger networks. And we can see the different output shapes here, and we can talk about the parameters. So 243 parameters. Those parameters are all the weights and biases that we can tune and stuff like that. So when you hear people, for example, GPT-3 and talk about like billions of parameters, that's what they're talking about, all the different weights and biases they can adjust. Okay, so actually it's relatively small. Okay, cool. And then we can actually, this is actually a technical one. You do have to have these libraries installed, which is not inside the learn environment, just so you know. But you can do a conda install, and you can see basically this. You might see this in like papers and stuff. Where they think, okay, this is like the different layers and like different inputs and outputs going through here. So it's basically this right here, just perform the picture. And so you can actually, it actually outputs this as an image right here. So you can actually see that image, and you can put that in your notebook or whatnot. So it can be pretty useful if you care about that kind of stuff. Okay, cool. So we can also look at the layers. So just know that there's certain layers here. No, these are just basically addresses to where those layers exist. I can get those specific layers. So this can be really useful for transfer learning. We want that specific layer and like do certain actions on it. Just kind of showing you this going on. And then we also have this weights and biases. We can get that first layer, right? So this can be dense 1 and get the weights, and you can actually see what those values are. So what's kind of cool is that this is actually randomly created and the bias is all 0. But as we train it, these values will change, right? And if I were to count all this stuff, this would be I think this should be 150 based on what was given out to right here, number of parameters. Okay, 150 after we consider all the weights and all the biases. Okay, cool. All right, so let's actually train this thing, right? It's like, all right, let's have the model, let's train it. So I'm just creating this as history, so that way I can kind of evaluate it later on. So it's kind of useful for us to do different plots and stuff like this. I'm going to do X-train. So remember we have our X-train data, our Y-train data. So basically what the true output's supposed to be. I'm going to do 500 epochs because why not? I got some time. Validator data. Basically this is going to be nice if you put validator data. Basically it will say, okay, here's your valid data, and it will compare it as it's training. So this can be really useful for you to evaluate how well it's doing as it's going through. All right. And we'll go ahead and run this guy. Okay. Oh, note that if you don't have validation data, you can do a validation split. So you can do the validation split within your model. In general, I would suggest determine your validation data ahead of time. That way you can have consistency. That way you know what the validation data are. And so if there's something weird that happens, you can at least look at the validation data and double check that everything's fine, or you can use it for a different model and such. So if you did it this way, it's going to be a little bit harder for you to pull out that information. Okay, cool. So let's run this guy. And oh, I didn't have X-train defined. What do you mean? That was anticlimactic. Oh, I never ran this. There we go. And I probably have to recompile my model now. No, I don't have to recompile, but this is probably fine. Why are you taking so long? There it goes. Okay. That took a lot longer than I thought it was going to take. All right, so let's go ahead. I'm using a Mac, that's why. I'm not on my Linux machine. All right, now I can run this and you can see here, boom, boom, boom. If you're a really complex model, this will you can actually see this like progress further along. But you can see here, if I look at this, minimize, there we go. You can actually see here some information. So this is the first epoch of 500, right? And you can see it took 1 second, it took 46 milliseconds per step. So this can help you get an idea of how quickly your model is training. It tells you the loss, so basically how big this loss is. This value can range from very, very large values. So know that 0.965 is kind of arbitrary. The important thing is that's going smaller and smaller. We can also see the accuracy because I put that as a metric, validation loss, and validation accuracy as well. So you can see this on the validation data. So note that the validation is not being trained on specifically, right? We're training on the training data. The validation data is just seeing how it does. However, you should treat your validation data as tainted now because you now are looking at it. So you shouldn't try to train off of that or test off, sorry, you shouldn't try to test off of the validation data. You also shouldn't train off of it directly at least. Okay, and so if you just scroll through here real quick, like you can kind of see these values get smaller and smaller. In fact, in this case, the accuracy is 100%. It's already reached, it's a very small data set. So you can see it already by like epoch 192, like I already have 100% accuracy on the true data. We can see that validation is still kind of fluctuating around. And technically this is getting, like this loss should always get smaller, like, or at least should be approaching smaller and smaller because that's how training works. It's never going to not get smaller. It doesn't necessarily mean your model's better, okay? Because it's based on just the training data. The really thing that matters is really the validation accuracy or the validation loss or whatever metric you're looking at for validation. Does that make sense to people? Okay, cool. All right, so do that through. We also could have set a specific batch. We could say, oh, use this batch of data to process it. But in general, you probably won't do that for most of your things that you're gonna do. You're probably gonna do something like this with model.fit. Okay? And then just to kind of show you guys what happened, we can see that the biases were all 0. You will now see is that the biases are all not 0, right? So these values now have changed and stuff, and these are the different weights it's been tuning over those past 500 epochs. Ooh, I said 10 to 15 minutes, but it's definitely going over, but I'll keep going. Sound pretty good? Okay, all right. Evaluating the trained model. So now it's like, cool, we got this model, it's trained, it's super, super cool. What do we do with it now? Like, oh, we get to investigate it, right? With just all machine learning algorithms and any inference and stuff like that, we should see how will it actually do. So what's cool is I saved that as history. So now I can actually pull up that history on here. So history.history, I have a data frame now. I can actually kind of do some extra stuff just to make things nice and easy for us to see. And you can see here, I can see now how well our model did over time. So on this x-axis is actually the number of epochs we had. So remember I did 500. So you can actually see on the model training, you can see the model, that neural network that was getting better and better. And you can see sometimes basically hasn't really done any much better for accuracy and then kind of bounces up a little bit and stuff. And the reason why this doesn't bounces up is I only keep the best model essentially. So that's why it's kind of like nothing happens and all of a sudden it boom goes up, boom goes up. If this was a more balanced model, you would see this, or more regularized model, you probably would see this a little more smoother, where you'd see little hiccups and stuff like this versus just straight line every single time. Okay, and you can see the validation accuracy. The validation accuracy, even though it got better and better by like 150 epoch, or the 100th epoch, it didn't really get any better than that. Even though the model accuracy was still continuing to get better and better. Not that accuracy should be the best thing you should use, but it's one of the metrics we can use. And so you can see is that validation is really the important part because this is going to be seeing where it trails off. So in reality, I probably should have stopped training right about here, like a little past the 100th epoch, because it's not really doing any bit better than that. This is what we'll talk about early stopping for optimizations, but it's important to kind of investigate this. So this is accuracy, but we can also do the same thing with loss, right? So you can see I'm using loss, validation loss, right? And the same idea here. And remember, we want loss to be low, right? Accuracy we want to be high, validation loss wants, or any loss wants to be low, right? And you can see validation loss is actually always going to be slightly higher. Well, I shouldn't say always, but will tend to be higher than the model loss, right? The loss function. And that's because the validation is not going to be directly, we're not training off directly of validation data, right? We're looking at saying, okay, we're training off of this blue line here, getting better and better. And validation is basically always going to be something different, right? So you would expect this. But the idea here is that you want, even though the loss is going smaller and smaller, you might want to investigate a little bit, saying when should we stop? Should we keep going through and all this stuff? So this is where you can see, but you can see this go over. If I'm overfitting, and I could probably do this myself, like if I made it more complicated, you'll actually sometimes see the validation loss. So this loss will keep going smaller and smaller, right? Which is what you expect. Validation loss might kind of go to the inflection point and start going up. And that's when you know you're starting to overfit. And this is why it's super important to look at this graph. I will tell you right now, if you're doing a neural network, you better have something like this, because people like give me results and they're like, oh, look, we trained it. It's like, yeah, but are you overfitting? And they're like, I don't know. And I'm like, see, that's what you should look at to see if you're overfitting. In this case, you might even argue you might be underfitting, which makes sense because my model wasn't super complex in that way. So it might be possible that we're actually underfitting under this stuff too. So that's kind of the idea of like what you would use this validation loss complexity graph. Okay, cool. Sound good? Any questions on this guy or this guy? Okay, cool. All right. So let's see real quick. What do I have? We could look at the overall loss from our test data after training the model was trained. After training, the model was trained. I don't know why I said it that way. All right. Oh, so we can actually evaluate on this new test data, right? So we have the model, we're done training, we want to test it on our data, right? This is usually done after you've done your stuff. You don't want to keep iterating on top of this if your test data is not good, because you are going to start getting biased as a person, saying, well, not even as a person, but basically saying, oh, it didn't do very well on the test data. Let's modify it so then it does do better on the test data. That's the problem, right? You're starting to modify it and go off this test data, and this should be like untouched data that should never, really be like you should only look at it and then you're done with it. You could have multiple models and then test it on all at once, like that test data, but you shouldn't have a test on the test data and then make a new model based on what you saw on the test data. Does that make sense? So those are good practices to keep in mind. We can even take for test data and actually look at what the classes are. So you can see here, like I mentioned, each of these are like one data point, right? So you put in the features in the neural network and it gives you this vector that's going to be the length of 3, right? And you're going to find the most, like the argmax, the maximum value, right? It's going to be this. So this one, for example, predicted it to be, class 0. This one's class 0. This one is class 2, or sorry, class 1, right? So 0, 1, 2. So you can kind of get the idea of like how this works. And you're like, well, that's cool, Victor, but like I want to know like I want to know what the actual value is, right? So you can do an argmax. One thing I'll note is that when they're really close together, like this guy, it's kind of interesting to look at this stuff too, because you can see it's like less confident, right? It's got 54 and 43. Those are relatively close together. So basically I had a confusion, like saying maybe it's like, I think it's number 3, like the 3rd row, but maybe it's actually the third column, but maybe it's actually the 2nd column. So that's where you can kind of investigate a little bit of like how different it is. Okay? But if you just want predictions, you can get the predictions like this. And you can see 0, 0, 1, 0, 0, 1. Okay. And that's how you can check this out. It's like, cool, we got predictions. And then we can say, hey, how far off were you? How far off were we? We can actually look at the predictions. Are they equal to these predictions right here, right? And then divide it by the prediction shape. So say, hey, we were by 83%, so that's our accuracy. Okay. And you can do all of the evaluation stuff too, but I just kind of did a really quick one. Okay. Any questions on that, these guys? Yeah. Thumbs up, thumbs down, sideways. How are we doing with understanding? All right, I see some thumbs up, maybe some going here and there. And this is where, like, as we kind of code around stuff, you can pick it up. When you're done with your model, you might want to save it for later. So you can actually do with Keras model.save, and I'll just save your model, including all the weights and stuff like that, and just save it off for later. So I can actually run this guy. Boom, my model's here, and you can actually check it out in my code, or not my code, my thing. You can see there's my model right here. So, and note that if you try opening this up, you're not going to really get anything useful. It's basically a compressed file for you to like investigate. And then for later, like, say, okay, now I want my model back. You can actually take this model, keras.models.load model, my model, and boom, I got my model now. And now I can actually do things like, actually continue training or do more predictions and all that stuff. So I can now use that model that I had previously trained. Okay, or maybe my friend passed me a model, said, hey, here's a model I already trained, take it, and I can play around with it, look at the different weights, modify it, or just use it as is, maybe for my web application or something like that, whatever I wanted to play it with. Okay, cool. All right, that's kind of all of Keras implementation. I kind of went a little bit over, but hopefully it was worth it. That way you guys can kind of see a little bit what's going on. I know it's a lot of information going through. So like the recording will be up at least. Like I like to say like that way you guys can like, I don't know about you guys, but I sometimes like watching recording sometimes because I can just like scrub through and like find the relevant information. So how there's Victor talking about, his babies or whatever, and like kind of scrolling through and whatnot. Not that I do that a lot. Okay, I don't know. Anyway, but now that we're kind of done, is there any questions at all? Yeah, feel pretty good. How are we feeling about all this? Oh, go ahead.
No. So next session, next study group, we're going to go over optimization of hyperparameters and all that.
That's right. So we'll talk about optimizations and like what that looks like. We'll also talk about overfitting, like how to avoid overfitting for our neural networks. They're very similar in the sense that we want to avoid over complexity. So we'll talk about that, but optimizations will also play with like how do we get to an answer quicker, right? And when we say get to an answer quicker, not just like say, oh, it works. It's also going to be, does it work and do we get there to a sufficient amount of time? There's some things we can do in that. So we'll talk about that next time. And if we have time, we'll probably start talking about convolutional neural nets or at least some deep learning applications. And we'll kind of continue that. Hopefully we can finish it up next session, at least convolutional nets. And that way, when we start Thursdays, not next one, but the one after that, we'll finish up any deep learning stuff, transfer learning, and then talk about NLP. Okay. Cool. All right, everyone. Cool. So I'll stop recording here. Where's my button? There it is.